Hello, everyone. Welcome back to the organic mechanism talk. And before we talk about the detailed reaction, again, I want to remind you that arrow pushing always shows the movement of electrons, always from nucleophile to electrophile. And today we're going to talk about the palladium catalyst coupling reactions. And we will talk about two reactions. One is a Suzuki reaction, and the other one is a Heck reaction. And the reaction named after organic chemist Suzuki and Heck, and both of them won a Nobel Prize in 2010. Okay, so that means the reactions are very useful. And first, we are going to talk about the Suzuki reaction. This reaction will have a halide. This is the halide, and the R here usually should be the vinyl group or aryl group, and the other coupling region is the organoboron compound. And the catalyst palladium 0 means oxidation state of the palladium is 0 actually. L means ligand, and you also need a base. Okay, hydroxide is the common base used, and then you will form a carbon-carbon single bond between this R and this R prime. So we call this cross-coupling reaction. We can see the two examples. First is this bromide. This is actually vinyl bromide, and then with this organoboron compound, an ethyl group is on this boron, and so this vinyl group and this ethyl group will actually coupling to form this new bond between this carbon and that carbon. So the product is this trans pentene. And the other example here is the iodobenzene. So now this time the R is actually phenyl group. And then the other organo compound or boron compound is actually have a vinyl group on the boron. And that is the part of the category. Okay. And then the coupling between this phenyl and this vinyl group will form the new product that is actually styrene. Okay, so you can see the single bond between this carbon and that carbon formed here. So another cross-coupling reaction. Now let's talk about the arrow pushing mechanism. I will use this first reaction as example. The reaction I just copy paste from last page, and we can see the first step is actually the palladium catalyst will do insertion between this carbon and this bromine. So this is the intermediate formed. This is the intermediate formed. And I just said this insertion is also called oxidative addition. Why it's called oxidative? Because palladium here, the catalyst is palladium 0, but here palladium is 2 plus. So the oxidation state increased from 0 to 2, so it's oxidation. Next step is the hydroxide actually replace the bromide to form this intermediate. And this intermediate will use the oxygen, the lone pair will attack this boron here. So basically the oxygen here is nucleophilic and the boron is electrophilic because boron has an empty p orbital here. So they will form oxygen boron bond, and the intermediate boron is a negative charge now because it accepts the electron one from oxygen. Oxygen get positive charge because it lost one electron. So next step will be the ethyl group. Ethyl group migrate to the palladium at the same time, break the palladium oxygen bond, and so that form a complex of the palladium. You can see the vinyl group and the ethyl group actually both connect with the same palladium catalyst. And the last step will be elimination. and it's called a reductive elimination because palladium here is 2+. It regenerates the catalyst, which is palladium 0. At the same time, this carbon and this carbon will connect, form the carbon-carbon single bond. So that will be the product, the trans 2-pentene. So this is the arrow pushing mechanism of this reaction. Okay, the other reaction should follow the similar mechanism. Okay, this is for Suzuki. And look at the Heck reaction. So Heck reaction also use palladium as catalyst, and also use a base. But this time you use triethylamine as a base. You can also use other base. And the first coupling agent is similar with the Suzuki. It is a halide. And the R here should be vinyl or aryl group. But the other coupling agent actually will be alkene with the electron withdrawing group. And this should be the transposition to the hydrogen, which will be replaced by the R. So the R here will replace this hydrogen and to form this alkene as a product. Now look at the mechanism here. The first, let's look at the examples of the reaction. First, we have iodobenzene react with this alkene. Actually is an ester. This ester is a common electron withdrawing group for the Heck reaction here. And this phenyl group will replace this hydrogen. This is a transposition to this electron withdrawing group, the ester. And then you will have this product formed. Basically, is this phenyl group replace this hydrogen here. That's carbon-carbon single bond form. And the base is triethylamine. Catalyst the same, palladium 0. The other example is actually this vinyl bromide and react with this ester. Actually, the alkene with the ester, kebutyl ester. And this hydrogen will be replaced by this vinyl group and to form this product. See the new bond formed between this carbon and this carbon. And this time the catalyst is the same, palladium 0, but the base is a potassium chloride, potassium carbonate. And so I will use the first reaction to show the arrow pushing mechanism here. First step is similar, it's oxidative in addition, or you can say insertion. Okay, the palladium will insert between this carbon and the iodine, and then from the complex, this complex will react with this alkene here. So the phenyl group will migrate or attack this carbon, and then the pi bond broken, the pi electron will attack the palladium. So the intermediate will be shown here. So that is this is the single bond formed from last step, and that's another single bond formed between palladium and the carbon from last step. And now this hydride will migrate to palladium again. At the same time, we'll break the palladium carbon bond, and the electron will push back to form the double bond here. So that is actually the product here. This is the major product. Also, you will have the byproduct is this palladium complex. So next step, you need actually regenerate the catalyst. And then the byproduct is hydrogen iodide. It's a acid, and this can be neutralized by the base. So this is the arrow pushing mechanism for this Heck reaction. And you might wondering why we need an electron withdrawing group at the transposition of this hydrogen here. So if you look at the mechanism, this electron withdrawing groups here, because that will make a reaction faster, because this step you need to use this nucleophile phenyl group is the nucleophilic, attack this carbon, which is electrophilic, If you draw the resonance, you will see this is actually positive charged. And then, so if you have electron withdrawing group here, actually this carbon will be more electrophilic, means this electron withdrawing group will pull the electron density from this pi bond, make this carbon more positive, more electrophilic. So the first step here will be faster. So the whole reaction will be faster and the yield will be higher. Okay, that's for Suzuki and Heck reaction, the arrow pushing mechanism. If you have any question, let me know. Good luck.